It's a pleasure to open the second Brazilian workshop on soft matter. We have a bunch of very selected, outstanding people here, and I'm very happy and excited about it, to see your talks and to discuss science with you. So before we start the first talk today, we have a short presentation by staff from the Instituto Principia, where we are here. So after that, we'll start the presentations. Thank you.
Thank you. Hello, everyone. Good morning. My name is Eduardo. I'm here on behalf of the Board of Directors of Instituto Principia, and it's a great pleasure to welcome you here on the second Brazilian workshop on soft matter. We wish you a successful event, and I'd like to inform you that Instituto Principia is open for receiving proposals to future scientific events, such as Congress and workshop. If you'd like to organize an event with us, please check the information on these QR codes. We will now play a short video about the activities of our institute. Thank you for your time and have a pleasure day.
O Instituto Principia é um centro de produção e difusão do conhecimento científico e de conexão da ciência com a sociedade. Com atividades científicas desde 1951, tem atualmente 3 programas de atuação relacionados à pesquisa, educação e divulgação científica. No programa de pesquisa, acontecem eventos internacionais sobre temas atuais para diversas áreas da ciência. No programa de educação, a Escola de Talentos oferece oportunidades de desenvolvimento pessoal e acadêmico a jovens que tenham grande interesse e altas habilidades para a ciência, oferecendo uma tutoria científica com pesquisadores renomados. No programa de divulgação científica, existem diversas atividades com ênfase para o público jovem, como o You Science, o cinema científico e publicações em várias redes sociais. Conheça, participe, amplie seus horizontes através da ciência. www.institutoprincipia.org.
Okay. So our first speaker today is Professor Edgar Zanotto from the Federal University of São Carlos. And Edgar is going to talk about fundamentals and applications of glass crystallization. Thank you so much for coming.
Thank you, Danilo. Danilo, 45 minutos, né? Você me avisa depois de 30 e depois de 40. Você vai sentar por aqui. Good morning. Let me find out how this. Okay, it's a real pleasure to be here this morning. I'm going to talk about my favorite material, glass. I'm not sure if glasses are soft matter or not. Below the glass transition temperature, they become rigid. Anyway, they're soft if you heat them up a little bit. Fundamentals and applications of glass crystallization. If you're really interested in this thermodynamic phase transformation that happens when any glass is heated, they will tend to crystallize to reach the thermodynamically stable state. So crystallization is a very key word in the field of glass. If you are interested, we have published a very, very comprehensive review paper on the subject with maybe 80 pages or so. So I refer everything I'm going to talk today, it's explained in more detail in this paper. Okay, just a brief introduction. If you take a very old glass book, this guy, George Morey, says that devitrification is a danger when you're making a glass. So making glasses means avoiding crystallization. Any supercooled liquid below the melting point tends to crystallize. So if you want to produce a glass, you have to avoid crystallization. That's it. It's simple as that. Avoid crystallization, you make a glass. Like if you have water, put water in a fridge, it will form ice. But if you cool it really fast, avoiding crystallization, you can produce glassy water or glassy any material. So it's a danger if you want to produce a glass. And uncontrolled crystallization is called devitrification. Now, you can also control the crystallization process. If you make a glass and then you heat treat the glass, you can control it and produce glass ceramics. Just for fun, I have a ring here, which is a glass ceramic. You can see, I'm going to pass it through, you can see a glassy matrix with crystals inside. This you can see with naked eye. Normally you cannot see with naked eye, but you can see crystals in a glassy matrix. This is a glass ceramic. It's a composite material produced through controlled crystallization of glasses. There are all sorts of nano or microstructures. You can see glassy matrix with crystals. And these crystals, their size, their shape, their chemical nature control all the properties of this material. Chemical, electronic, magnetic, mechanical. Oi? Alô? Alô? Mais para cá. Alô, alô, okay. Can you hear me? Yeah, okay, thank you. 1 minute more in my talk, okay? So, you can control these type of microstructures to design your final material to achieve desired properties or combination of properties. So glass ceramics, there are many glass ceramics all around that you do not perceive, like the substrate of hard disks in your computers. Most of them are made of glass ceramics, artificial teeth, or cooktop plates, or even large telescope mirrors. They're made of glass ceramics because of their special properties. For instance, what's the property of these cooktop plates? 0 thermal expansion coefficient. We all learned that if you heat up any material, it will expand. While there are tricks that you can do, produce glass ceramics with 0 thermal expansion coefficient, so they will not break by thermal shock. And they are also transparent to infrared. Or, for instance, these artificial teeth, they have exactly the same hardness as natural teeth to avoid abrasion of the opposing teeth. Or they are same color, good chemical properties in the mouth, etc., etc. So there are machinable materials. There are many glass ceramics around that most people do not perceive. Even the projector lamp of the data show is made of glass ceramic. Okay, and these materials are produced by controlled crystallization of glass. Some cooking pans like this one, they're still transparent because the crystals are nanometric, very, very small crystals inside, but this is a crystalline material, not glass. So anyway, it's a long story. So glass ceramics, they depend on this microstructural design, and you can have combination of properties. For instance, you can have a bioactive material with much harder and tougher than normal glasses. Even the displays of the modern iPhones, 14 or 5 or 15.0 iPhones are made of glass ceramics, no longer glasses, transparent glass ceramics. They're much more abrasion resistant and shock resistant. Okay, so if you look at the keywords in glass research, the most used keyword is crystallization. And then if you sum up with crystal nucleation, crystal growth, or glass forming ability, this is the most frequently used keywords in the history of glass science. So important is this field. Now, I am aware that most people here are not familiar with glasses, so what is glass? And there's a very interesting article published a few years ago by the Royal Society of Chemistry. Do you really know what glass is? I have been playing games with glasses for many years, and I'm still not sure if I know what glass is. But I can give my shot. If this is the most famous plot for glass science, if you have a liquid is thermodynamically stable above the melting point. You have a liquid forever, it'll be a liquid forever. Now, if you cool down a liquid, at a certain stage, it will crystallize. Now, if you avoid crystallization by cooling it fast enough, you enter a region called supercooled liquid. This is a metastable state. I mean, this supercooled liquid would love to crystallize, but it needs certain time. If the cooling rate is fast enough, it will not crystallize. And you keep coming down here in temperature, coming down, and the viscosity increases and increases and increases. At a certain stage called the glass transition temperature, the material will become a rigid substance that we call glass. So glasses are defined only below the glass transition temperature. And they're rigid. They will break. They will shatter. They are rigid materials. But their structure is exactly the same structure as the supercooled liquid. So glasses are frozen liquids without crystallizing. Temporarily frozen liquids. They're not forever. Because if you wait, well, just before I tell that, if you heat them up a little bit, they will easily crystallize. Now, if you come back here at the temperature, say, a few degrees below the glass transition, glasses will relax, or their structure will accommodate. All glasses are relaxing. These glasses here are relaxing. Of course, if you are well below the glass transition temperature, if you are here at room temperature, it will take a long time. They will relax, but will take a very long time. You cannot wait this. So normally, you heat up a little bit just below the glass transition to follow up the relaxation process by measuring any property. All properties of glasses change with time. That's why they are not true solids. They will change with time and come back to the supercool liquid again. Then they're soft matter again. They're liquids. If you wait a little bit longer, they will also crystallize. All glasses will eventually crystallize. It's just a question of time and how far you are below the glass transition temperature and become a crystal. Okay. So before they fully crystallize, there is the birth of the first crystalline nucleus. So crystallization takes place by nucleation growth. So the first stage is crystal nucleation, and I'm going to spend the rest of my talk now trying to understand the early stages of crystallization, that is the birth of the first crystalline nucleus in any supercool liquid. You might be here below the glass transition or above the glass transition. It doesn't matter. It just takes longer. But this all things that happen above TG also take place below the TG. So glasses crystallize even below the glass transition temperature. All right. So this is my 2 cents on what glass is. There are many definitions in the internet. You can ask, what is glass? What's the definition of glass? There are many. This is my favorite. Glass is a non-equilibrium. It's not a thermodynamically stable state. It's a non-equilibrium, non-crystalline state of matter. Of course, the structure is amorphous. The structure of glasses is similar, very, very similar to the structure of their isochemical liquids. Same structure. They all spontaneously relax to the supercooled liquid state. That's why they're unstable materials. And the ultimate fate is to crystallize. This is my favorite definition, although not all authors agree with this definition. There are other definitions in the literature. Funny enough that when we submitted this paper in 2016 to the Journal of Non-Crystalline Solids, which is a journal specialized in glasses, it was rejected. And I fought a lot with the editors at the time to get this paper published, and they sent it back to other reviewers. And after 3 rounds, it was finally published. And now it's the most downloaded paper ever in the history of this journal. You know, so if you have your papers rejected, but if you believe in your ideas, fight for it. This is a true story. Anyway, so there are several theories to understand the early crystallization states. The classical nucleation theory is a very friendly theory that many people use. So the theory is very simple but elegant. If you have a liquid, a supercool liquid, below the glass transition, you wait a little bit, fluctuations will form. You know, heterophase fluctuations will form and dissolve. And this equation says that, this is from Gibbs, you know, the work, thermodynamic work, to form a critical nucleus of radius r, let's assume that they are spherical for simplicity, you know, you have a positive contribution of the surface energy, because if you have a crystalline nucleus, you have a new interface forming in the liquid, so you have a positive interfacial energy. You also have strain energy, because the density of the crystals are different from the density of the liquid. So you have some local deformation, strain energy. They're both positive, but you have the volume-free energy is negative because the crystals always have lower energy than the liquid. So overall, the interesting curve is this curve here. If you plot the free energy, the overall free energy, the Gibbs free energy versus radius, this is the resulting curve. If the fluctuations are smaller than the critical radius, they will dissolve back. They form and dissolve to decrease the energy. If they're larger than a critical radius, it will grow, and then you count as a nucleus, a crystalline nucleus. This is a very simple but elegant idea proposed by Gibbs many years ago at a certain temperature. If you change the temperature, you change a little bit this curve, but the same concept applies. So you need to reach, any fluctuation, you need to reach a certain critical size to be able to grow, right? So that's the idea. So this critical radius, the critical radius here is just the interfacial energy divided by delta G. Delta G is the free energy difference between the liquid and the crystal. It can measure by calorimetry. This thing here cannot be measured. There is no equipment to measure the interfacial energy between a critical nucleus of a few angstroms and its surrounding liquid. So you can calculate theoretically with several assumptions, or you can fit nucleation rate data to the equation, the final equation, to get the interfacial energy, but in principle it's unknown. It's an unknown parameter, unfortunately. Anyway, let's take a look on this. This is a real computer simulation, MD simulation of barium sulfide in a certain temperature. Vídeo, por favor. Fluctuations are forming and dissolving. The green dots are crystalline fluctuations. They're forming, dissolving, forming, dissolving, forming, dissolving, until a critical size. So a critical size is reached, then they start to grow. So these simulations, they confirm Gibbs' ideas on the fluctuations forming and dissolving, forming and dissolving. This is the process of nucleation. And if you can do that by MD simulations, you can compute the time to form the first nucleus at different temperatures. And then you can calculate nucleation rates. So that's what can be done. You quench your liquid to a certain temperature, and you wait a little bit, the first nucleus has formed. Then you melt the whole thing again, and do another experiment, the first nucleus is formed. It's a stochastical process. You have to repeat this several times. By doing half a dozen of experiments or so, you can compute the average time to form the first nucleus in your supercooled liquid. And then you change the temperature, you do these things again. In this way, by MD simulation, you can infer the time to form the first nucleus and the nucleation rates. But before I show you results, let me just dwell on the equation. Oops. Take a look here in a moment. This classical expression is very simple and elegant. It shows that this is the rate, the number of critical nuclei that form per unit time, per unit volume. The unit is like crystal nuclei per cubic meter per second. This is the nucleation rate at a given temperature. It's just the diffusion coefficient in the supercooled liquid, and W star. See, W star is that work for critical nucleus formation from that curve, which is the surface energy to the third power divided by delta G to the second power. And the other things are constants. It doesn't matter at the moment. They're constants that can be calculated. The key properties are the diffusivity and the thermodynamic work for critical nucleus formation. If you can measure independently this quantity here and this quantity here, you could then calculate nucleation rates and compare with the experimental data. Unfortunately, we cannot measure the interfacial energy. There's this unknown parameter, which is very annoying, and this is unknown. So the best we can do is to fit, say, this equation to nucleation rate data for some systems, and then leave sigma as a fitting parameter. But it will get better towards the end of my talk. So this is the expression, and then there are several assumptions. Of course, as most of these theoretical models, you have to assume that the driving force, the delta G, for a nano-sized crystal is the same as the driving force for a macroscopic crystal that we measure in the lab, that the interfacial energy is independent of temperature, etc., etc. There are several assumptions, but with all these assumptions, this is the steady-state nucleation rate. This is the diffusion term. If you measure diffusivity somewhere, somehow, and then the W star, you can calculate the nucleation rates. However, if you're dealing with, say, pure metallic nickel, you can measure the diffusivity of nickel. You know, simple substances, there are ways to measure the diffusivity. Now, if you're working with a silicate glass with 10 components, the diffusivity of what? It's very complicated, and there are barely any data. So most people, if you're dealing with glass-forming materials, with a polymer, with an organic molecules, you don't know exactly the diffusion coefficient. So most people assume that the Einstein worked on diffusivity also. With many things he did, he demonstrated that the diffusivity of molecules in a liquid are inversely proportional to the viscosity. This is KT, the jump distance, 1, 2, 3 angstroms, and this is the viscosity. So if you measure the viscosity, the diffusivity is inversely proportional to the viscosity. This is the Stokes-Einstein equation. So most people assume that this equation is valid in all situations, and then you can measure the viscosity of your liquid. This is easily measured in the lab, and then calculate the diffusivity. So we take care of this. We measure delta G by calorimetry. So we have only one adjustable parameter, and then you can test the theory. Now I'm talking about making a glass by fast cooling, and then heating this glass and waiting until it starts to crystallize. That's the kind of experiments that you do. You first make a glass, and then you heat it fast and measure the nucleation rates. Okay, and this is the kind of microstructures that you get. See like the ring that's going on around. You see the black area is still glassy, and crystals start to form. So you can count these crystals with optical microscopy if they're micron size, or electron microscopy if they're nano size. But you can count this. Count. You change the time, you count. You can measure experimentally. I'm not talking about MED simulations now. Experiments. You can measure nucleation rates. And these crystals are really beautiful, and you change the time and temperature, etc., etc. It's a long period of work, but you can measure this. Let's see another video, please, of a real crystallization. This is not MD, this is real crystallization of a particular glass-forming material. See? These crystals, they formed very fast, and then they started to grow. This is the final microstructure. This is a magnesium aluminum silicate, a glass-forming material. All right. So, if you have then the viscosity for the diffusivity, and you measure nucleation rates, and you measure delta G, you can test whether this theory works or not. And for the younger crowd here, why do we scientists bother in building up and testing theoretical models? What's the objective of science? The main objective of science is to understand, explain, and if possible, predict phenomena. So that's why we need theoretical models, to understand what's going on, to explain, and if they work well, we can use theoretical models to predict phenomena, rather than measuring all the time, which is really time-consuming, dangerous, costly, etc., etc. Theoretical models are the basis of science. If they work always, then they become laws. But first stage is to build a theoretical model. This is a theoretical model. Anyway, let's test whether this theoretical model works. So, CNEP can be tested, leaving one fitting parameter. Testing the theory. Okay, the first guys to test, more or less in the 50s, early 50s, they were able to measure nucleation rates in liquid mercury. Mercury is a metal, which is liquid at room temperature. You can cool it down and measure nucleation rates. And they are able to measure nucleation rates. See, two sets of experiments here. This is just a linearized plot of that equation. It's the log of nucleation rates times the viscosity divided by T versus 1 over T delta G. It's just a linearized form of the equation. Okay, good straight line. Let's then extrapolate here and compare the value of the, let me go back a little bit, of the pre-exponential factor with the theoretical value. Go back a little bit. Yeah, we now want to, we plugged in the viscosity, the viscosity for this part, the delta, 1 over delta G square for this part, and want to compare the value of the theoretical. This theoretical value can be calculated, so we compare the extrapolated value from the experiments with the theoretical value of the pre-exponential, using sigma as a fitting parameter. So we extrapolate here, get the pre-exponential and compare. Guess what? 7 orders of magnitude discrepancy. Not 7 times, but 7 orders of magnitude. People said, well, but these experiments were very crude. They were measuring, this is only 2 degrees Celsius, a very long extrapolation. They're only 2 degrees Kelvin, so they're not a definitive test of the theory. 10 years later, John Hoffman was then in the National Bureau of Standards, was able to measure nucleation rates in a polymer, polyethylene. 3 degrees Kelvin. Well, 3 degrees Kelvin is better than 2, 50% better. Nice straight line, extrapolated. Guess what? The discrepancy went over to 12 orders of magnitude. 3 degrees Kelvin is not a good test. Somebody else has to measure in a better way. Metallic glasses were discovered in the 70s. So the first people to measure, forget the noise here, get the straight line, extrapolate it, and compare the theoretical and experimental values in this metallic glass. 20 orders of magnitude. I gave this talk, this part of this talk many years ago in the USA, and this American professor from New York called David Pye says, he was a big guy, Edgar, you should consider submitting a report to the Guinness Book of Records. This must be the worst theory ever. So thank you, Professor Pye. I will consider your suggestion, and I'll tell you the story in the end, what happens with the Guinness Book of Records. Okay, so 20 orders of magnitude. Now, well, there's a lot of noise here, etc. This is not a good test. Let's do a good test. So, glass making people oxide liquids are very good glass forming materials. Metallic glasses are very unstable. So let's try to measure nucleation rates and that's when I started to work, 1977 or so. Tem mais 10, no? In this area. So anyway, people have measured nucleation. This is nucleation rates versus temperature divided by the melting point, just to show them in the same plot. You see, very nice nucleation rate data measured at wider ranges of temperature, which would provide, in principle, better tests. And these are beautiful crystals that we are able to produce and count precisely these crystals in different glasses. This is from my lab, actually. And very nice, still in linearized form, very nice straight lines, which can now be much better extrapolated, and very curious to see if these better data really provide a better test of the theory. And guess what? Went up 30 orders of magnitude. You see the temperature dependence. This is the calculations, and the data is here. The temperature dependence is quite well described, but not the magnitudes. And there's some noise here, but forget this, it's another problem. But overall, this is what we found, and many people did this for other systems, barium disilicate, soda lime silica, always these huge discrepancies, always. And see the discrepancies here in orders of magnitude, up to 55 orders of magnitude. This must be really the worst theory ever. I was then considering to write a nice report to the Guinness Book of Records. So, enormous discrepancy. However, we had one adjustable parameter. In all those papers, sigma is unknown. It's adjustable parameter. And so none of those were definitive tests of the theory. So we had this one adjustable parameter. Second thing, nobody had measured the diffusivities. Everybody was using the Stokes-Einstein equation, using the viscosity as a proxy for the diffusivity. So there are two problems, at least, with these kind of tests. Now, how can you bring back theory and experiments into agreement? You can force fit each data point. You can force fit, what's the interfacial energy to bring back agreement? You force fit. So by force fitting, we get this curve here. Forget what happens below TG. It's much more complicated below TG, but for the time being, forget that. I do not have time to dwell on these complications, but you get a nice straight line showing that interfacial energy is not constant. In the previous test, the interfacial energy was taken as a constant. It varies a little bit with temperature, say from 0.15 to 0.16 joules per square meter. This is joules per square meter. It's an interfacial energy. And this little bit to the cubic power within the exponential. You remember, it's the exponent of interfacial energy to the cubic power. brings back theory and experiments into accord. However, this is a force fitting. This, again, is not a test of the theory. Of course, you can publish papers with this. Any of these tests is a new paper, and that's how I made my career anyway, publishing papers on these tests. They say, oh, it doesn't work very well, but you can publish it. Okay, now, so by the pandemic years, the situation was like that. You know, maybe the interfacial energy, and the interfacial energy is a thermodynamic parameter, so it should vary with temperature. It's reasonable to think that it varies with temperature. But let's try to do some MD simulations. The pandemic years came, the labs were closed. So what can I do? Let's do MD simulations. And then MD simulations, I have shown this video already. You can then compute the time to form the critical nucleus in simple systems for which reliable potentials are available. The potentials have been tested with many other types of properties. There was a very reliable potential for barium sulfide. That's why we picked barium sulfide, just because the potential was good and tested in many other situations. So let's see if we can measure these things. We could measure. And then also the diffusion coefficient. This is good news because from the MD simulations can give you the true diffusion coefficient also. So we can get the diffusion coefficient. In this case, barium and sulfur, they are about the same. So we just took the average because they are almost the same. Then the material crystallizes, the diffusion coefficient drops. But this is the supercool liquid area. We get the nucleation rates, diffusion coefficients, and then there is one missing thing, the interfacial energy. How can we get the interfacial energy? These guys in Sweden had a very nice idea. You can insert an artificial critical nucleus in a supercool liquid and test the growth velocity, not the nucleation. You have nucleated artificially. Test the growth velocity. If the growth velocity is negative, it's because this cluster is dissolving. If it's positive, it's growing. So by playing games with the size of this artificial cluster, we can get the critical size at different temperatures. If we can get the critical size, we can calculate the interfacial energy because delta G is known for most of this system. So by MD, you measure actually the critical size and then measure delta G and calculate the interfacial energy. So now we have a way to avoid the assumption about the interfacial energy, and then we have published several papers, all these in the pandemics, and Leila, where is you? Leila is here, she did a lot of the simulations. That lady from Iran, who was a postdoc here for 4 years, her grant finished now. Unfortunately, FAPESP only allows 4 years, so she is looking for another position. If you are interested in MD simulations, you can do all this stuff. But there's this Leila, and this is zinc selenide. You see again the idea of forming, dissolving, forming, dissolving, forming, dissolving. A critical nucleus then forms, and the material grows, and this is the final result. Long story short, nucleation rate computed by MD simulation, and then these are computed by MD simulations and calculated by classical nucleation theory using these parameters derived independently, like the diffusivity and the interfacial energy derived from MD simulations plugged in the classical nucleation theory, and this is very, very nice description of nucleation rates within a factor of 2 or 3, which is nothing compared to the 50 orders of magnitude that we had. And for other systems, so zinc selenide, barium sulfide, etc., But there's always a reviewer that says, well, these are all calculations. You have to compare with experimental data. So we found a system, nickel, for which there was a very reliable potential. Many people are interested in nickel, in the metallurgy field. And some people had measured nucleation rates in nickel. So let's try to do MED simulations and compare with measurements. So these are our MED simulations, brute force MED simulation, spontaneous nucleation, the blue circles, then calculations from CNT using the seeding technique to get the interfacial energy. So these are all calculations, very nice agreement. And finally, people had measured here. Let's see the measurements here. Measurements and our data here. Very nice agreement between, we cannot measure it here, but these are extrapolations using the parameters derived from MED simulation plugged in the classical nucleation theory. So just to complete my final slides, because this is so nice, nucleation of water. I see there are papers about water in this conference. So outro vídeo, por favor. This is very nice. MED simulations of water crystallization. See how beautiful this is. Anyway, many people have measured nucleation rates in water because this is the most important liquid for us. Experimental data from different authors, and then our MED simulations, this is with ICTP-SAIFR, and predictions of the classical nucleation theory for water. So with that, I finish saying that the combination of experimental years of work with MED simulations performed during the pandemic years shed light in this very old and complicated problem, which is so important for metallurgy, for mineral formation, for glass ceramics. Crystallization is a very important phenomenon in nature anyway. And the key thing here was that collaboration with many authors along many years. And this is my take-home message for the young attendees of this workshop. Thank you very much. Oh, meu anel. It's back here.
Thanks so much for the beautiful talk. Questions for Edgar?
Thank you, very nice talk. You had many orders of magnitude discrepancy, and you could finally come to an agreement by changing diffusion parameters and also the surface energy.
Yeah.
By how much? Because I'm wondering, is it also orders of magnitude difference in the diffusion coefficient to fix that or not?
No, it was a small difference in the surface energy. But the surface energy, if you recall, the interfacial energy here, instead of being a fixed parameter, let me go back here very quickly. Oh, here. So the fitted value of the interfacial energy probably was, I don't know, 0.16, the fitted constant value. If you allow it to vary from 0.15 to 0.16, and this is in the cubic power, this is in the cubic power here. Let me go back. here. This is to the third power here inside the exponential. It's unbelievable and slightly temperature dependent. And the diffusion coefficient was like two orders of magnitude off or so. But this was a little bit off, maybe 30% off, and temperature dependent. Yes, yes.
Thank you. That was up here.
Yeah, okay.
Thank you. That was a very instructive talk. I'm wondering, have you seen the crystallization of supracrystals from nanoparticles, and does this follow these tendencies? And maybe somehow related, what do you think about crystallization experiments on colloids?
I have read about crystallization experiments on colloids. I never worked myself with colloids, but I have seen very, very elegant crystallization experiments of colloids. I think people have even also tested the theory by comparing calculated values with you can measure crystallization rates in colloids, but I don't recall their outcome. But I don't have particular personal experience with crystallization of colloids. What was the first question?
Kind of related, supracrystallization of nanoparticles? Which is kind of a practical example of crystallization of colloids.
Oh, if you start with nanoparticles. Because here, all these cases are nanocrystallization. Yeah. All these cases. You start with a glass, and it's always nanocrystallization. Of course, if you wait, these nanocrystals will grow up to micron size. But I never worked starting with a nano particle. That's what I was discussing with Leila this morning during coffee break. You can use boundary conditions in an MED simulation, boundary conditions for a nano condition or for a macro condition and see the difference. But we never did that.
Thank you.
Thank you for the great talk. Is there a known theory for the temperature dependence of the interfacial energy?
Yes, yes. There are empirical models that predict a positive temperature dependence for the interfacial energy. I'm sorry for not showing that, but yes, and they agree. Yes, very good question.
Here. Besides the temperature dependence, you also have the curvature dependence of the surface tension. So if you have really these nanoscopic systems, I mean, you should also worry about what is going to be the curvature dependence.
You were right, but they are embedded. You can also, there's the Thoman equation, and so you can also, both dependencies are embedded in this fitted, when I show a fitted evolution of the interfacial energy with temperature, there are both effects embedded in this dependence. But you can do the same kind of calculations just assuming a curvature dependence. Yeah. Because the nucleus size increases with temperature. That's why they're embedded, they're interrelated.
Yes, thank you for the very nice talk. I was triggered by the last calculations that you did on ice nucleation. There is a whole discussion on this Mupemba effect.
Yeah.
That warm water crystallizes faster than cold. Is it real, and can you see it here?
I have read about this effect. We did not see it. But
because it could be hidden in this surface free energy term that is temperature dependent,
exactly.
Right?
This is the most recent work that water is very complicated. If you work with water, it's a nightmare of complications. There are many phases possible, etc., etc. So I have read about the moment. We did not see it in our, not so detailed simulations so far.
Thank you very much.
Thank you.
Okay. Stand here.
Thank you very much for the very nice talk. Yeah, I had two quick questions. One is related again to the interfacial free energy. As far as I remember, in the classical nucleation theory, the interfacial free energy is one of a flat interface.
Yeah.
So there are numerical techniques actually to compute it, such as direct coexistence, that are very trivial. And why did you think of computing direct already the interfacial free energy with a curvature dependence? Because you are using this seeding method that is implying a curved surface.
Yeah, if you use the value for the flat, for the macroscopic crystal, say a macroscopic crystal, you have these huge discrepancies.
Yeah.
We did this for Lennard-Jones. For Lennard-Jones systems, it's very simple potential. We calculated the variation of interfacial energy with temperature, extrapolated to the melting point, and it more or less agrees with the value for the flat interface theory. I can send you this paper to you.
Okay.
Yeah.
And I have another quick question concerning the ice nucleation part. I mean, depending on the water model you use, there is a huge discrepancy even within just numerical simulations when computing the ice nucleation. Then when you compare to experiments, things go even worse. So you are showing these huge error bars, but which water model you used actually to simulate?
The so-called MW.
Oh, the MW is very coarse-grained water model.
The MW model was used for this simulation, but you're right. Other models will give completely different values. This is for the MW.
Okay.
Let's see again. For the MW, it worked rather nicely. Go quickly.
But that's, strictly speaking, not real water. It's sort of colloidal water, meaning it's coarse-grained water.
Yeah, yes.
Okay.
It's a coarse-grained water. The error bar, I tell you the error bar, is because we did not know exactly the value of delta G for water. Oops.
Delta G for MW model has been computed.
Yeah, but if you take the computed model, you have this curve here. If you take the experimental values, then you have this error bar here. These are taking the experimental values of delta mu.
MW is also another issue, that the melting point is quite shifted.
The melting point is shifted.
Yeah. So
It's
one
true.
has to reshift everything to compute.
Yes, it was shifted. But water, as you say, water is not the very best system to test the theory, I think.
Okay, thank you so much, Edgar.
Thank you very
thank
much.
him again.
Thank you.